Good evening. Good evening. It's my privilege and my pleasure to welcome you to this year's Rank Lecture of the European Conference on Visual Perception. The Rank Lecture is endowed by the Rank Prize Funds, which are a beneficiary, I'm told by John Mullen, of the Merseyside, because Joseph Rank, who founded the Rank Mills from which the fortune came, did a lot of his business at mills along the Mersey in the 19th century, and his son, J. Arthur Rank, who founded the Rank organization, which endowed the funds, owes its wealth in part to this area. So it's fitting that the lecture should be here. The Rank Lecture has been a part of ECVP for 8 or 9 years now, and it is a lecture to recognize one of the leading lights in the field. And this year, it's my pleasure to introduce my colleague and friend Marisa Carrasco, who is a professor of psychology at NYU, where I happen also to be. So Marisa has been at NYU for 20 years. Before that, she was on the faculty at Wesleyan, and before that, she trained with Ron Kinchla and others at Princeton University. She has done a variety of important pieces of work in a number of different areas of perception. Her central interests are in attention and in perceptual learning and the interaction between those things and the control of action. When Marisa started in the field, attention was an active field of study in visual perception, as many of you know, but it was largely measured by its influence on perceptual judgment. And what Marisa realized and pioneered was the idea that attention not only affected your perceptual judgments, but actually affected the way in which you perceive things, the way that things actually seem to you as an observer. And her most influential and I think important work in the last 20 years has been on the subject on which she's talking tonight, which is how attention affects visual perception in the title and early vision on the slide. Now, as part of the Rank Prize lecture, she receives this handsome plaque with an intrinsic value of 0, but lots of fun. Let's take it off to the side where it can be seen, and let's. And I will now take this away and sell it on the street while we all listen to Marisa tell us about attention and perception.
You want to take this with you?
I will take anything you
so
want.
that I don't trip. Thanks. Hello, everyone. Thanks so much for being here. I want to start by thanking the organizers, Marco, Sophie, Kate, Alexi, Johan, and Rebecca. Thanks so much for the organization. It's a pleasure for me to be here, and it's lovely to have this beautiful place. And Bo, actually, everybody can hear me. I know, someone asked me if you would be too jealous, and I said, just a little bit. This morning he told me he was over. So today I want to tell you about how attention affects early vision. And as you know, each time that we open our eyes, we are confronted with an overwhelming amount of information. And despite this fact, we have the very clear impression of understanding what we see. And this requires selecting relevant information out of the irrelevant noise. So one way that I think about attention is that it often turns looking into seeing. The real computer is there, so I'm clicking the wrong thing. Here we are. So what I want to do today is give you a little bit first of an overview of some critical ideas in attention. Then I want to tell you about some of the effects of attention on contrast sensitivity, and finally some of the effects of attention on spatial resolution. So many of you may be familiar with this quote by William James. I've seen it many, many times. Everyone knows what attention is the taking possession by the mind in clear and vivid form of one out of what seems several simultaneously possible objects of trains of thought. Focalization, concentration of consciousness are of its essence. It implies withdrawal from some things in order to deal effectively with others. And as often as this is quoted, I think it's a very unfortunate first sentence. Everyone knows what attention is, because unfortunately, for a long, long time, the word attention has been used without really defining what we mean by attention. And I will revisit that. On the other hand, of course, the quote is insightful, and in particular, I'm going to revisit the last sentence. It implies withdrawal from some things in order to deal effectively with others. This is later going to be seen as trade-offs in processing. Being an experimentalist, actually, my favorite slide is this one from Helmholtz. He published in 1867 in Physiological Optics this quote about attention and this report of what I think is the first empirical observation on covert attention. It's a curious fact that the observer may be gazing steadily at the two pinholes and holding them in exact coincidence, and yet at the same time, he can concentrate his attention on any part of the dark field he likes, so that when the spark comes, he will get an impression about objects in that particular region only. In this experiment, the attention is entirely independent of the position and accommodation of the eyes, or indeed of any known variations in or the organ of vision. Thus, it's possible simply by a conscious and voluntary effort to focus the attention on some definite spot in an absolutely dark and featureless field. So again, to my mind, this is the first empirical report of covert attention, which is what I'm going to be talking about. But before I do that, I just wanted to mention this graph, which with my former student Antoine Barbeau, we just published recently. And this is the number of publications on visual attention that appear in PubMed that have visual attention either in the title or the abstract. And as you can see, half of the articles have been published only in the last 10 years, since 2005. But more interesting for me is is this dotted line that I added here, which is the observation. They had asked me to write a review of attention for vision research in 2011. And at that time, I discovered that in vision research, which back then, or it's, as you know, one of the premier journals in the field that deals really with perception, there were only a handful of articles on visual attention before 1990. And as a matter of fact, by 2000, there were only 50 articles published in vision research. Journal of Vision came soon thereafter, and of course, these are the publications in all the journals. But one thing that is interesting to me is that really it's in the last years that we consider this aspect of attention affecting, as Tony said, the very essence of visual perception. So, Jack, if you could, please. I'm going to ask you to look at the screen carefully. Just keep looking, and you're going to notice 1 or 2 or 3 or 10 or 20 things that are changing as you look. And you should feel free to put your eyes wherever you want. And I like this very much because it just changed right in front of you. This was the original image, and this was the final image. Okay? You can look wherever you want. The other day I gave a talk and someone said, I saw the change, and I laughed because last time I counted there were 34, and then I got bored. But if I put them side by side, you can look wherever you want, and every change happened right in front of you. And very slowly, nothing was blinking, there's no tricks. So how come we have this idea in our phenomenology is that we really see everything in front of us, and we miss so many details, even when they happen gradually in front of our eyes? Well, one of the ideas that has been put forward in a long time in cognitive psychology is the idea of limited resources. And that concept that has been with us in cognitive psychology since 1960 really has been having some reality more lately when we relate the idea of limited resources with the bioenergetic cost. So we know that there's a high energy cost of neuronal activity that is involved in cortical computation, and that limits our ability to process information. And this is because there's a constant overall energy consumption that is available to the brain. It changes through our lifespan, but at every point in time, it's constant. The neuronal metabolic cost depends on the spike rate, and the cost of a single spike is high. And that's why the average discharge rate of active neurons determines how many neurons can be active concurrently. In 2003, Peter Lenny concluded that the number was about 1%. There's a more recent paper that suggests that maybe it's 5%. But 1.5, the main idea is that the brain needs some machinery to allocate energy according to task demand. And attention is proposed to be a key mechanism that allows to manage such energy. Adaptation, of course, is another key mechanism. But today I'm going to talk about attention. Now, when we talk about attention, we talk about visual selective processing of information. So the processing of the input is enhanced by knowledge of the world, by the behavioral state of the organism, and by sudden changes in visual information. One thing that is important to keep in mind is that attention is not necessarily a unitary process, but what is common to the different processes that I'm going to mention is that they prioritize processing of some information over other. So in the lab, we study several processes of visual attention. And today I'm going to talk in particular about covert attention and the spatial component of covert attention with its two subsystems, exogenous and endogenous, which I will define in a moment. Many others here have studied feature-based attention, as we do. We also study temporal attention, as well as the interactions of covert and overt attention. And as I mentioned, more recently, we've been concentrating on studying the effects of covert attention and perceptual learning. But today, I will concentrate on the effects of spatial covert attention. So let me try to illustrate this. Let's imagine that you are here. Well, actually, imagine that you're at the start of the New York Marathon, and there's hundreds of runners on the bridge. It would seem that we're capable of processing all information simultaneously, but our ability to process details in the periphery is rather limited. So if, for example, you were looking at this person that is in the middle, in reality, the representation in your resolution would be more like this, because we know that the quality of information severely decreases as you move towards periphery. Now let's imagine that you're there because one of your friends is running, and you know that he's going to be running on the right side, as he's not the fastest of runners. So you may want to keep your eye here because you're wondering, who is this guy and is he waving at me? While at the same time, you want to deploy your endogenous spatial attention to another location. So this is one way in which our system can solve processing information in different regions of the visual field. But of course, not all the changes that happen depend on where we want to allocate our attention endogenously. There are things that happen in the environment. For example, someone may have taken a picture and there's a flash, and those transients in the environment are going to make us allocate our exogenous spatial attention in an automatic way. And I will be happy to explain more about the automaticity. Some of it is going to be mentioned, but for now, I want to make clear that there's two different processes within covert spatial attention. So in all the instances that I'm going to be talking about today, your eyes are directed at someone. So I'm gazing. Let's imagine that I'm looking at Tony right now, but I want to monitor Bo to see if he continues being really jealous. So I may deploy my endogenous attention there, and something may happen, like Marina just tilted, and that attract my attention, and exogenous attention may be deployed there. So the first one, endogenous attention, is voluntary or goal-driven, whereas exogenous attention is involuntary or stimulus-driven. Endogenous attention is known to be flexible. There are many studies that show that it scales with Q validity. That is, we can proportionally allocate X resources to a particular location, whereas exogenous attention is automatic and it does not scale. It seems to be like an all or none process. Endogenous attention has a slower temporal dynamics. It takes about 300 milliseconds to be deployed, and once you deploy it somewhere, it stays there. And this is also the case in monkeys. Whereas exogenous attention, it has faster dynamics, but it's transient. It peaks at 100 milliseconds, at about 100 milliseconds, and dies shortly thereafter. And we know we have some information about the cortical networks that mediate these systems. Until recently, we thought that cortical networks mediated endogenous, whereas cortical and subcortical mediated exogenous attentions, but there's some recent studies that show that endogenous attention is also mediated by subcortical structures. And we know more about the role that feedback from frontoparietal areas play in early vision with regard to endogenous attention than to exogenous. Another thing that I want to mention is that in most cases, these two subsystems have very similar effects in perceptual performance, but not in all the cases. And today I'm going to illustrate some of both. Similar effects of contrast sensitivity, but under certain circumstances, different effects on spatial resolution. And in reference to the comment of James that said everybody knows what attention is, I think actually that we have advanced in the field of visual attention when instead of using the term without really defining it, people have made an effort to define what is meant by attention, to operationalize it. In principle, in an ideal situation, when we study attention, we want to keep both the task and the stimuli constant across conditions while we manipulate attention rather than infer its role. Of course, we want to monitor observers' eyes and to make sure in the case of covert attention that they are fixating. And it's important that the cues that we use to manipulate spatial attention, or whatever manipulation is used, convey only information that is orthogonal to the task at hand. Some of the earlier studies conveyed certain probabilities in detection tasks, and unfortunately many of the results could be interpreted not as an effect on perception, but an effect on a decision-making mechanism. But now we know that it's important to have cues that convey information that is orthogonal to the task. So to start talking about the role of endogenous and exogenous attention, I'm going to concentrate. We know that it improves visual discriminability in many tasks, such as those of contrast sensitivity, spatial resolution, and motion. We also know that modulates subjective appearance and that it speeds information accrual. And this has been reviewed in a number of papers. But today I'm going to concentrate on contrast sensitivity and spatial resolution. I'm going to briefly mention a couple of studies on appearance. So in terms of contrast sensitivity, when we look at a scene like this, any natural scene contains first and second order contours. So many regions in these pictures are bounded by luminance-defined contours, such as the two walkers on the walkway. And these contours can be signaled by linear spatial filters from the retina to primary visual cortex, which are selective for spatial frequency and orientation. For example, however, these linear systems cannot detect changes in visual attributes other than luminance. For example, the different sections of the walkway differ in the local orientation of the wooden slats. But the average luminance is relatively constant across the different sections. So the patterns that are defined by changes in textural attributes, such as local orientation, contrast, and spatial frequency, are not visible to linear filters, and those are commonly referred to as second-order patterns. So texture information is vital for segmenting the retinal image into distinct regions as an initial step for object recognition. Now, if we look at the model, this is what Landy, Graham, and others have called a backpack model. A typical model of visual processing with parallel pathways has parallel pathways for first and second order stimuli. In the top path, luminance-defined stimuli, the boundary between the two pedestrians and the walkway, are signaled by this linear filter. On the bottom path, there's a filter rectified filter cascade that is sensitive to second-order stimuli. As I mentioned before, the texture-defined boundaries between the different regions of the walkway. And both first and second order are going to be combined later on at a different stage, at a later decision stage. So today I want to illustrate some examples of studies that we have characterized how covert attention affects contrast sensitivity in both first order and second order stimuli. If you were in John Robson's talk this morning, you saw this image, and you have seen it in all the perception textbooks there are. So as you know, here we have the contrast going from more to less on the y-axis as a function of spatial frequency in a log scale. And you all know that what is inside this curve, or depending on your eyes, how far you're sitting, and your age, that curve is going to be modified slightly. But we know that everything that is inside of this curve is going to be the window of visibility, and what is outside of this curve is outside our window of visibility. So some years ago, with one of my first graduate students, we asked, is it possible that attention could expand the contrast sensitivity function? i.e., is it possible that it affects the window of visibility? And these are the results of such study. So this was an orientation discrimination task. Many of the studies I'm going to talk about today are about orientation discrimination, which is contingent upon contrast sensitivity. And in the top row here, these are results. I show what is the contrast that was needed for observers for different spatial frequencies to attain a given performance level, say 82%. And as you can see, of course, the contrast is less than intermediate frequencies, and it has to be higher at higher frequencies and lower frequencies because our sensitivity is less. The news of this study is what happens if there was a peripheral cue before the target. And as you can see, for each single frequency, now we need less contrast in order to attain the same performance level, which indicates that contrast sensitivity has been improved. Now, at that time, there was a lot of debate in the literature about the mechanisms that could underlie that. I won't get into the details today, but there's good evidence for both signal enhancement as well as external noise reduction. And I will be happy to answer questions about that. So now that we established that contrast sensitivity actually is improved at the attended location, then the next question was, what happens at the unattended locations? Does contrast sensitivity remain the same, or is there actually a trade-off in processing? So in order to study this, we had a very simple paradigm. Imagine that you're fixating at the screen, and randomly either a neutral cue appears in the center or a peripheral cue appears adjacent to one of the two stimuli that will appear there shortly. And at the end, there's going to be a response cue indicating to the observer which location he or she has to report from. So in this case, it will have, she will have to say that the gabor is tilted to the right. And the timing is going to be critical because we want to make sure that the timing between the cue onset and the display onset is about 100 milliseconds to be at the peak of the exogenous attention system, as I mentioned before. And in this case, just to summarize then, if there's a match between the pre-cue location and the response cue, that's a valid cue. If there's a mismatch between the cue, the pre-cue and the response cue, that's an invalid cue. And neutral, which we've done several varieties of neutrals, is just a control that would allow us to observe two things. Benefits that come about by the valid cue, as you can see here. This is a ratio of sensitivity when we compare the valid over the neutral in blue, so everything above 1 means an improvement. And for these different parafoveal and perifoveal eccentricities, we get significant benefits, and at the same time, we get significant costs at the invalid location. So even for this very poor display, just two boring gabors on the screen, there seem to be mandatory trade-offs in processing. Now, once we saw that we could have this good experimental task, we wanted to see what would be the neural correlates. Today, I was putting this screen, and I remember this is a quiz. This is your perception speaker of 1993. Does anyone remember? Not the young people, Tony, Bo. Okay, this is Peter Lenny. So that was the day that we were inaugurating our scanner. And as you know, fMRI indexes brain activity by measuring blood flow. We know that oxygenated blood flows to brain regions with more neuronal activity, and the scanner is going to pick up the differential magnetic properties of the oxygenated and the deoxygenated hemoglobin. Now, thank you. What you can see on the left is the way that we and many obtain retinotopy. We have very systematic ways of mapping the visual field so that we can see exactly where activity is in terms of radial and eccentric stimulation. And after we do retinotopic mapping, then we can see all the brain areas, the areas of interest in this talk are going to be V1, V2, and V3, at least at the beginning. And this is just to remind you of the great help that we have when we study early vision, because we have this beautiful retinotopic representation of the world. The other thing that is going to help our studies a lot is that we know that bold response increases with contrast. And we're going to take advantage of that, because once we establish what the effects of attention are on contrast sensitivity, now we want to then evaluate whether when we attend to a particular stimulus, even though the contrast of the stimulus remains the same, we're going to get enhanced bold activity. And this was the first study of exogenous attention in the scanner. A little trick was to really separate the stimulus evoked activity, which is going to be projected to dorsal areas, from the cue, which is projected to ventral areas. And in order to do that, we simply presented the cues above the horizontal meridian and the stimuli beyond. And as you can see here, even, this is the fovea, even in V1, where there's a continuous representation of the field, we could assure that there was no overlap. And as you can see in V2 and V3, we get stimulus evoked activity, whereas we get at V3A, we start getting a common representation, which corresponds to what we would expect. Now, this is important, but even though we have this spatial control, obviously there's always the possibility of some subthreshold summation. So we designed a little control experiment that is very similar. This is the pre-Q trial that is similar to what I've told you before, except that in this case, one Gabor is going to be tilted and the other vertical. And the important thing here is that we're going to have a post-Q trial. So this is important because we took advantage of probably the worst enemy, or the worst thing that we have in fMRI, which is the sluggishness of the hemodynamic response. But in this case, the sluggishness of this hemodynamic response was useful because compared to the Q target stimulus interval, it's long. So I want you to notice here we have the Q before the stimulus, and here we have the stimulus before the Q, the post-Q. And so the response from a region that responds to both the Q and the target cannot differentiate the order of these two because of the sluggishness of the response. So thus any different effect between the pre-Q and the post-Q cannot be attributed merely to sensory summation and can be attributed to attention. So this is the performance of the observers while they are in the scanner. We simply replicate what we've observed outside of the scanner, that is, performance is better for the valid pre-Q, indicated in red, and it's faster to make sure there's no accuracy trade-offs than in the other conditions, invalid pre-Q and the two post-Qs. Once we have established that performance is the same in the scanner, then we look at the bold time series, and the fMRI response was estimated by the convolution here. The activity was marginally higher in V1, but significantly higher in V2, V3, V3A, and V4, which is not shown here. And we calculated an attentional modulation index, whereby we see the peak of the valid pre-Q minus the peak of the baseline over the sum. So a value of 0 would indicate no difference, a value of 1 would be the maximum. And as you can see here, there's an increased index that progresses through the visual areas. Now, in the case of endogenous attention, this has been interpreted as feedback from prefrontal areas and parietal areas that trickles down, and that's why the effect is less pronounced in early visual areas. Since here we're talking about exogenous attention, it could be a feed-forward mechanism that simply inherits the activation that has been accumulated before, and that results in steeper contrast response functions across different visual fields. Now, we know that there's this neural correlate, but the question is, what mechanism is underlying these changes of attention in contrast sensitivity? And you may be familiar with a long controversial debate in physiology of how endogenous attention affects neuronal responses to different contrasts. So on the left here, we have contrast gain, and on the right, response gain. This is a normalized response as a function of log contrast. And what people have found is that attention increases neuronal responses by multiplying the stimulus contrast by a constant gain factor. The effect is largest at intermediate stimulus contrast, and that's why this is displaced to the left. In contrast, response gain is characterized as an upward shift of the constant response function. So attention increases neuronal responses multiplicatively by a response gain factor. And the effect is larger at high stimulus contrast. Now, other studies have found a combination of both, and even that within V4, for example, there's a subset of neurons that respond with contrast gain, a subset with response gain, and yet a third group that responds with activity gain or an effect throughout. Now, these patterns of response have also been found in psychophysics. So in general, for endogenous attention, we and others have reported a contrast gain shift, whereas for exogenous attention, we and others had reported a response gain, but there are other studies that have seen mixed results. So what we wanted to see is if there was any way to try to reconcile these different findings in neurophysiology and in psychophysics. And to my advantage, sorry, sometimes I have three things to move because my slides are actually back there, so here we are. My colleague and friend, David Heger, with John Reynolds, proposed this model of the normalization model of attention, which tries to address why some studies yield contrast gain and others response gain. The idea of normalization stems from the normalization model of visual responses, which was introduced in the 90s. And normalization is a canonical computation. Many people here have worked with it, certainly many of my colleagues and friends at NYU. And what is particular about the normalization model of attention is that in normalization, responses of neurons are divided by a common factor that includes the sum activity of a pool of neurons. Now, in the normalization model of attention, David and John did a lot of simulations where they identify two key parameters that could underlie the differences in contrast gain and response gain. And those parameters are the size of the stimulus and the size of the attention field. And one thing that is particular about this normalization model of attention is that it enhances the stimulus-evoked responses before the normalization. There are other models that have been proposed by Jeff Boynton and by Mansell, where they would affect both the numerator and the denominator. So they would either always yield contrast gain or response gain. So what is unique about this model is that actually can affect the numerator and the denominator independently. So I'm not going to dwell a lot on this slide because it would take a lot of time, but I just want to tell you that in this model there's three main components: the stimulus drive, the attention gain factors, and the normalization factors, which together result in the population response. In the stimulus, so what we see here are these four squares that depict neural images. In each point corresponds to the response of a neuron, which can be specified with certain receptive field center and orientation preference. So in this case, these neurons care about the position of X, but don't care about the orientation. And the gray level is going to indicate the stimulus drive for each neuron, which is largest for the neurons whose preferred positions and orientations match the stimuli. Now, the stimulus drive is going to be modulated by these attentional gain factors, which depend on the range of the attended locations in the case of spatial attention, or the attended features in the case of feature-based attention. And the attention gain factors are going to be multiplied point by point with the stimulus drive. And the normalization factors are computed from the results of the multiplication by pooling over space and orientation, which are shown by this asterisk, through convolution with the suppressive field. And the output firing rates of the population are computed by dividing the stimulus, the stimulus drive by the normalization factors. This results in a population response that is amplified at the site where attention was deployed. So the stimuli are the same, attention is deployed here, and here we have a boost on the representation. Now, the key idea of the model is that the stimulus and the attention field size are going to reshape the distribution of activity process across the population of neurons, and they are going to shift the balance between excitation and suppression, yielding either a contrast gain or a response gain. Now, the intuition of the model is that there's going to be a stimulus drive that is divided by a suppressive drive and a constant. So if the attention field is large, which I'm indicating by this red dotted light, relatively to the stimuli, which is indicated by these vertical bars and is lower, then attention is going to turn up everything in the model equation, and it's going to have the same effect as just turning up the contrast. This is going to result in contrast gain. In contrast, if the attention field is small, as here on the right, in relation to the stimulus size, which is larger, then it's carving out the region in the surround, and it's going to decrease the suppression in the denominator, and this is going to result in a response gain. So the interesting thing here is that now we had a model that could allow us to test some predictions, and that's exactly what we set out to do. So in this paradigm, it's very similar to what I have shown you before. We are going to compare exogenous attention on the left with endogenous on the right. The main key difference is that in exogenous attention, the cues are uninformative, and people know this. They know that it's equally likely to be a valid cue or an invalid cue, whereas in endogenous attention, they're informative cues. So when there's a central cue indicating one particular location, 75% of the time is going to be correct or is going to be valid, and this is to incite people to allocate attention in that direction. And then we're going to compare endogenous and exogenous attention under the parameters that allow us to mimic the predictions of the model. So in this case, we have a large stimulus, indicated here, with a small attention field. So here you see the large stimulus, and actually we put little distractors surrounding to ensure that people actually try to attend only to the stimulus and not to the surround. And what we see is that in both cases, in exogenous attention, where we had obtained response gain before, indeed we obtain response gain again. Here we plot D prime as a function of contrast. These are Naka-Rushton functions. In black, you see the neutral function. In red, you see the valid, and in blue, the invalid. And as you can clearly see, there's a very pronounced change at the max, but no change, or the asymptotic level of performance, but not in C50, which is the intermediate point between the lower asymptote and the upper asymptote. So this is consistent with what we had reported before. The interesting thing is that this is also the case for endogenous attention under these parameters, where we and many others had found contrast gain before. So again, if we have a large stimulus and small attention field, now we're going to find response gain also for endogenous attention. Now, conversely, we want to have conditions, according to the predictions, in which we have small stimulus, which is inside a large attention field. And here we have one stimulus on each hemifield that can appear in any of these 5 locations. These dotted white marks are only for illustration purposes, so people knew that there was uncertainty, and then they would have to open their attention field in order to be able to process these stimuli efficiently. And what we find first is that for endogenous attention, where we had expected contrast gain, indeed we find contrast gain. Now you see that performance shifts at C50 at the intermediate point, but there's no significant differences at the max, the prime max, or the asymptotic response. And again, the critical question here is what is going to happen now to exogenous attention, where before we had obtained contrast gain. And as you can clearly see, is within these conditions, we get a very clear signature of contrast gain and no change and the max. So if we put this together, it seems that we can mimic one or the other pattern according to the stimulus size and the attention field size. Now, one thing that is interesting is that I've been telling you that we manipulated the attention field size. To manipulate the stimulus size is very easy. To manipulate the attention field size, not so much so. And we were not convinced ourselves that we had done that without running into some circular reasoning whereby we found what we wanted and then we concluded that we manipulated what we wanted to manipulate. So what we did was test with an fMRI protocol to measure the attention field size. This slide is for my friend Bo Watson. He knows why. So here we have the observer looking at a fixation point. There's a pre-cue, 2 stimuli are going to appear. Observers are going to do the 2AFC orientation discrimination task that they did before. And there's going to be 2 critical conditions. In one of them, the stimuli are small, and again, they can appear in any of these locations. And in the case of exogenous attention, the cue would co-vary with the target. And this is to create uncertainty. In the other condition, the stimuli is only going to appear at the location that corresponds to the middle location here. And these placeholders are going to indicate to the observer exactly where the stimulus is going to be. And then we're going to only compare the performance for the stimuli that appear in the third location so that the stimulus display is identical and it's only the uncertainty that has changed. And what we found is that the attention field size with uncertainty, which is plotted on the y-axis, is greater than the attention field size with no uncertainty on the x-axis for 9 out of 10 hemispheres. So when people are spreading the attention, when they're opening the attention field size, we actually see larger activation in terms of extent. So this allows us to conclude that indeed we could manipulate both stimulus size and the attention field size, and to conclude that exogenous and endogenous attention enhance performance consistent with contrast gain or response gain depending on the relative size of the attention field and the stimulus. We also found that the spatial uncertainty manipulation is effective. The attention field size, as indicated by bold response, is larger with than without uncertainty. And this proves that, as was predicted by the model, attention multiplies the stimulus-evoked activity before normalization. So now we have an idea of the mechanism that may be taking place here. And the next question we had was, sorry, before I go there, I just want to show you that this is also the case for second-order contrast. So just very quickly to revisit here our scene. We're going to manipulate stimuli here with very similar paradigms. We're just going to manipulate the stimuli in such a way that now people are going to report, also in an orientation discrimination task, to the following stimuli. And here you can see that we can manipulate independently the first-order carrier spatial frequency, which can be low or high, and we can cross that with a second-order modulator of spatial frequency, which again can be low or high. And by having these stimuli, we can isolate the contribution of first-order and second-order contrast. And when we manipulate only second-order contrast, we find very similar results to what I just showed you before, both for exogenous attention and for endogenous attention in conditions when we expected response gain. We find very clear signature of response gain. So now we have shown that indeed attention affects first order and second order contrast. And then the next question was, what happens to the subjective phenomenology? What happens to our subjective appearance. So we know in performance studies that it affects our contrast sensitivity, but the question is that accompanied by our subjective experience? As some of you may know, this is a very old question in psychology and physiology. People like Boone, Helmholtz, Mack, and Titchener suggested that yes, attention would intensify the sensory impression. James also suggested that that would be the case, but he said that attention would never lead us astray. And Fechner, the father of psychophysics, said no. But interestingly, in one of the writings of James, he said the subject is one which will repay exact experiments if methods could devise. So at some point, we read that, and we decided to devise such a method. So this is going to be very similar to the paradigm I've shown you before, except here there's going to be a cue in one location, in the other location, or neutral. There's going to be two stimuli that appear simultaneously, but here, instead of presenting a response cue to the observer, telling her where to respond to, the question is, what's the orientation of the higher contrast stimulus? So we know that attention affects orientation discrimination. We just use it as a cover, so to speak, to see really what was the perceived contrast. And we had different standards, Gabors, and different tests that encompass the whole range and different spatial frequencies. And to summarize these results, when we plot the number of times that people reported that the test is higher than the standard as a function of the contrast of the test stimulus, in black we can see the neutral response. When the test is skewed, we see that now there's less contrast is needed to attain the point of subjective equality, and vice versa, when the standard is skewed, now less contrast is needed to obtain that point of subjective equality. And we have conducted many studies to rule out alternative explanations. If you have any question about them, I'll be happy to tell you. Here I just present one where we did exactly the same stimulus, but we interleaved trials in which the stimulus onset asynchrony between the cue and the stimulus was 500 milliseconds instead of 100. Because as I told you before, exogenous attention is transient. By 500 milliseconds, we should expect no effect whatsoever, and that's exactly what we got. We also wanted to know, and this summarizes the results, so if you were fixating here and you were under the experimental conditions, the Gabor to the left would be perceived as the contrast of the Labor to the right. So we know that exogenous attention affects subjective appearance, and then we wanted to know if that would be the case with endogenous attention too. So we modified slightly the paradigm. We put an RSVP, or Rapid Serial Visual Presentation task, just to ensure that observers would allocate their attention to one location. And we always indicated with a valid cue the location where an X would appear, if it would appear. And it was present 20% of the times. And then we piggybanked, so to speak, and we put two stimuli thereafter, and we asked exactly the same task. Give us the orientation of the stimulus of higher contrast. So having performance for the RSVP allows us to ensure that observers attended, and indeed their performance was better. And then we look at the similar curves as I showed you before, and again we see very clearly that here when we pre-cue the test, we need less contrast, as you can see, for the point of subjective equality than for the neutral, which in turn needs less contrast for the standard. And here's another control experiment. We simply invert the instructions. If people have any bias to respond to the location of the cue, we would have get the opposite results, and as you can see, the results mimic each other or match each other perfectly well. So now we know that attention affects contrast, and then we wanted to see, or perceived contrast, and we wanted to see what are the neural responses that underlie this apparent contrast increase. So as I told you before, there's contrast gain, there's response gain, and also there's an input baseline that has been reported. And what we plot here on the right is in standard contrast the effect that we would expect. So if it was a contrast gain change, we would expect the contrast effect to increase as a function of the standard contrast. In a response gain, we would have this exponential function, or we would have a constant effect in the case of an input baseline. And doing this experiment at many, many different standards, what we find is the best fitting model prediction, which indicates clearly that the effect of attention is constant or close to constant across ranges. And this is the normalized response of the simulation. And what we find is that this input baseline increase can explain the effects of attention on perceived contrast. So to summarize this part, we've shown effects of contrast sensitivity on first and second order contrast. I show you that it also affects appearance, and that we have behavior improvement that correlates with an increase in fMRI signal in striate and extrastriate cortex. And we find that these changes in performance and appearance are consistent with a normalization model of attention. Now, just to finish, I want to mention some studies of the effects on spatial resolution. And as you know, spatial resolution declines with eccentricity. Here we have the receptor field size for macaque, and you can see that the size increases with eccentricity and across visual areas. And on the right, we have the population receptor field size that have been obtained with fMRI, and we can see that it's there's a very nice and close correlation. Now, in terms of attention and spatial resolution, we know that attention affects performance in visual search, acuity, and crowding, and we also know that it changes the appearance of spatial stimulus attributes. From the neurophysiology, we know that there's changes in receptive field size, structure, and position. And so with one of my former postdocs, Katarina Anton-Ersleben and I, we wrote a paper in which we tried to link the psychophysical and the neurophysiological evidence. And I'm just going to tell you a little bit about this. So one thing that we know is that receptive field size can shrink or expand with attention. This is part of Katarina's dissertation, and a lot of this work has been done in Stefan Troyal's lab. This is a condition where a monkey is fixating, and this is the receptor field size. In the monkey is trained to attend inside the receptor field. Now you see that the receptor field shifts and shrinks a little bit. And conversely, if now the monkey is, in this case, is fixating, and this is the receptor field size, but now the monkey is trained to attend besides the receptor field, now you see that this receptor field expands. So knowing this and putting back some studies from my lab, we tried to see if we could relate those findings to the psychophysical findings. So what you see here first on the left is visual search performance for some features and conjunction searches. Here you see reaction time as a function of eccentricity and error rate as a function of eccentricity. And not surprisingly, when the stimuli are standard, that is when all of them have the same size, you see that reaction time and error increase. Now, if performance in visual search is related to resolution, then we can magnify the stimuli according to the cortical magnification factor, as indicated here in green, and now you see that these two curves are very flattened. So knowing that that was the case, and given some findings that we had from attention and spatial resolution, we reasoned that probably we would get similar effects if instead of magnifying the stimulus, we simply had people attending to the location of the upcoming target. And as you can see here, the reaction time and the errors increase, but when people attend through this pre-Q, now we see that the functions are fairly flattened. So this suggested to us that probably attention was increasing spatial resolution. And then in a number of studies with Yafa Yeshurun in my lab that were later replicated by Goya and collaborators with monkeys, they found that monkeys and humans have very similar functions. So for acuity task, if you have a Landolt acuity that is presented at 3, 9, or 15 degrees, the acuity threshold in ArcMinute is always higher for the neutral than for the cued location. That's the case for macaques, as is for humans. And in a later study, we showed that this is the case both with exogenous and endogenous attention, but in addition to having acute advantage or a benefit for the cued location, we also have a pronounced cost for the uncued locations, again indicating that there are very pronounced trade-offs with exogenous and endogenous attention. But then we thought, well, heightened resolution is optimal most of the time, but not always. There are situations in which heightened resolution is not ideal. For example, here, if you're driving under foggy conditions, in case you leave Liverpool, then you have, for example, this Seurat painting, in which you can see that if your resolution is too high, like in any pointillism painting, your perception is not going to be the best. And likewise, we can see here that if your resolution is too high, perceiving Einstein is going to impair your perception of Marilyn Monroe. Is that clear for everyone? If you cannot see both of them, just take your glasses off or squint, one or the other. So we took advantage of a task that had been established in the texture segmentation that shows that when we plot performance as a function of eccentricity, the performance peak does not occur at the fovea, as it is the case for most static tasks, but rather it peaks somewhere in paraphobia. And performance decreases at more peripheral locations because now the resolution is too low. And interestingly, it also is impaired at the fovea because now the resolution is too high. And this is just to remind myself to tell you that we know it's been established in physiology that there's an inverse correlation between the receptor field size and the spatial frequency preference. The smaller the receptor field size, the higher the preference. So with Yafa Yeshurun, who's here in the audience, and my first grad student ever, we conducted this experiment, and here what we plot is percent correct as a function of eccentricity for a small texture scale that goes up to 12 degrees. Then we simply sit observers twice as close, now with doubled eccentricity. And what I would like you to see with the blue curve is that we replicate what others have obtained with texture segmentation. The interesting thing here is that when people attend with this exogenous cue, we improve performance at periphery and we hamper performance in the center. And this is a function of the texture scale. So between 2 and 4 degrees of eccentricity, highlighted in blue in both graphs, we can either improve performance or impair performance as a function of the scale of the texture. So this is a very nice demonstration, if I may say so, that exogenous attention indeed increases spatial resolution. And more recently, with another graduate student in the lab, with Antoine Barbeau, we saw if in this task we would also see trade-offs in processing. So the black line and the red line are simply replications of the study I just told you about. The blue line is interested because this is for an invalid cue. And for both small texture scale and large texture scale, now we see not only pronounced costs in terms of where the peak is displaced and the central performance drop for the valid cue becoming more pronounced, but now we have a paradoxical situation in which diverting attention actually improves performance. And that is because the resolution is being lowered. But then we said, well, this is interesting for exogenous attention. What happens with endogenous attention? Endogenous attention has been postulated to be a more flexible system. Again, here, if you see a Seurat, or if you see a Salvador Dali rendition of Lincoln or Gala, or both, depending on where you're seated, we know that at some points in time, it may be more beneficial for the system to either increase or decrease resolution. And indeed, here I'm plotting the experiment that I told you about with Yafa Yeshurun with exogenous attention, and more recently with Yafa and Barbara Montaña in my lab. We found that for different scales, with endogenous attention, performance always increases. So here's a very clear difference of the effects of exogenous and endogenous attention. And then we set out to understand why it is the case. And we did this study, which will be the last study I will tell you about before I wrap up.